Swayam Prabha. Digital India. Educated India.
So, in the last class, we looked at self-adjoint operators, basically matrices, and by that I mean real symmetric matrices, okay, because real symmetric matrices are A equals A transpose. Adjoint was defined as the transpose, and if it's equal to the original matrix A, then it is self-adjoint, okay. The operator is equal to the adjoint. So, then we looked at the properties of the eigenvalues and eigenvectors of the self-adjoint operators, and we looked at the fact that the eigenvalues will be real. We looked at the fact that the eigenvectors are going to form an orthogonal set, but not always you have self-adjoint operators, right. So, we want to understand how do you what are the properties for regular operators which do not have to be self-adjoint. Basically, if A is not equal to A transpose, okay, what are the properties of the eigenvalues and the eigenvectors? Eigenvalues you already know, eigenvalues of A and A transpose are the same, but what about eigenvectors? Is there a relationship between the eigenvectors? That is the question, okay. So, that is what we are going to focus on. Is not equal to A transpose, okay, and what are the properties of the eigenvalues and eigenvectors for A not equal to A transpose. So, basically we already saw that the eigenvalues of A and A transpose are the same, okay. Of A and A transpose are equal, okay. So, now I want to find out whether there is any relationship between the eigenvectors of A and A transpose. So, what I will do is I will first derive and then tell you what the relationship is in English, because I think that makes things more clear, okay. So, consider this eigenvalue problem for A, which is A ui equals lambda I ui, okay. So, this is the definition of the eigenvalue for A. This is how you find out this thing. Now, for A transpose, I am going to call the eigenvector V so that there is less confusion, and I am going to call this Vj. So, corresponding to the eigenvalue lambda j, the eigenvector of A transpose I am denoting by V is Vj, okay. So, there are n eigenvalues lambda 1, lambda 2, lambda n, V1, V2, V3 are the eigenvectors of A transpose, U1, U2, U3 are the eigenvectors of A, okay. So, basically the set ui is the set of eigenvectors of A, and set Vj set of eigenvectors of A transpose. Okay, and let's keep life simple. Let's just say we have n eigenvectors, I have an n by n matrix, I have n eigenvectors. Now what I want to do is, since now there is a possibility that the eigenvalues can be complex. In the earlier case we showed that eigenvalues were real, okay, and we were working with a real inner product. But now because eigenvalues come from the roots of a polynomial, you could have a complex eigenvalue. Complex means imaginary, a plus ib, okay, and therefore we have to now work in the complex inner product space. We cannot work in the real inner product space, okay. So here the eigenvalues can be complex and we work in the complex inner product space, okay. So what I am going to do is, I am going to take the complex conjugate of the second equation here. So remember A is real, the elements of A are real, okay, because this is coming from modeling a physical system. So elements of A are real, and when I take the complex conjugate of this, what I will get is A transpose Vj bar equals lambda j bar Vj bar, okay. So this is basically looking at the complex conjugate of the second equation of the transpose equation. So this is complex conjugate of the second equation, and A has real elements as it comes from a physical problem, okay. I mean it will have some velocity, pressure, viscosity, all these are real quantities. What I am going to do now is take the inner product of this with Vj bar on the left and of this equation with ui on the right, okay. Let me call this equation 1, this equation 2, this equation 3. Take the inner product of 1 with Vj bar on the left and 3 with ui on the right. What I want to do? Yeah, on the right. Okay. So I will do what I write, Vj bar on the left, Vj bar with AUI equals inner product of Vj bar with lambda IUI, and the other guy is A transpose Vj bar with UI equals inner product of, what is it, lambda j bar Vj bar with UI, okay. Now I am just going to subtract the 2, and you have to understand that by definition of adjoint, okay, this is this thing here, this is by definition of adjoint integral Vj bar A ui is equal to inner product of A transpose Vj bar ui. That is how we define the adjoint, right? It should be true for any vector. So, this is the definition of adjoint. So, when I subtract these two, this will cancel, okay, and I get 0 equals, and now here what I am going to do is take out the lambda outside, because the lambda is hitting the second variable. When I take it out, it comes out as it is. Here the lambda is with the first variable. When I come out, I will get the complex conjugate of that, so I get lambda j, okay. So, what I am going to get is lambda I minus lambda j inner product of Vj bar with ui, okay. So, because of the way we define the inner product, the first one we complex conjugated when I had a scalar. So, when I have the scalar here, lambda I comes out as it is. When I have the scalar here, lambda is a scalar, it is an eigenvalue. I will take out the complex conjugate, it is already complex conjugated, so I get lambda j. So, what this means is, if lambda I is not equal to lambda j, okay, if lambda I is not equal to lambda j, then the eigenvector of the ith eigenvalue is perpendicular to the orthogonal to the complex conjugate of the eigenvector of the jth eigenvalue of A transpose, okay. So, if I is not equal to lambda j, ui ith eigenvector of A is orthogonal to complex conjugate of Vj, the jth eigenvector of A transpose. Yeah. Where did I miss the bar? Here. This one. Below this? No, it is not lambda bar j. That is what I am saying. It is not lambda bar j, because it is lambda j. Because the way we define the inner product, remember, is no, this is lambda j. That's what I was trying to explain, but it's good you asked me the question. See, if you remember the axioms the inner product has to satisfy for the complex space, okay. Inner product of u comma alpha v, I said, was going to be alpha times inner product of u with v, and inner product of alpha u with v is alpha bar u with v, okay. These are the axioms. Why is it like this? Because inner product of u with v is defined as, this is, I am going to put, recall, okay, is defined as sigma ui bar vi, okay. So, because alpha is the second guy, there is no question of taking complex conjugate. Alpha is the first guy. I have alpha bar if it is here, and when I take it out, I get conjugate. Because this is already conjugated, it gets unconjugated, okay. So, yeah, is it clear? So, this is equal to, by definition, ui alpha vi, and this is equal to, by definition, sigma alpha bar ui bar vi, because alpha is the first variable, okay. Instead of alpha we have lambda. So, I take the complex conjugate of this first guy here, take second guy, no complex conjugate, only the first guy is complex conjugated, because this is how I defined my inner product, And if alpha is sitting here, I'll complex conjugate. If alpha is sitting here, I don't complex conjugate. So basically, when you have a general matrix which is not self-adjoint, okay, you will have n eigenvectors for A and n eigenvectors for A transpose, let's assume, okay, because that's an assumption. I think I can erase this. So for a general matrix, let's say we have n eigenvectors for A and n of A transpose. So what are these? U1, U2, Un, okay, and then V1, V2, Vn, okay. So now what is the relationship between these two? If I mean I'm ordering it, so this one corresponds to lambda 1, lambda 2, lambda 3, okay, that is the order you have to maintain. So U1 is the eigenvector corresponding to lambda 1, U2 is eigenvector corresponding to lambda 2. Same thing here, lambda 1, lambda 2. What I have just shown here is that U1 will be perpendicular to the complex conjugate of V2 through Vn, okay. If these are real, then there is no issue, you do not have to worry about complex conjugate, but it could be complex. So U1 is perpendicular to V2 through Vn, U1 with V2 bar, U1 with V3 bar, U1 with Vn bar is perpendicular. U2 with V1 bar is orthogonal, U2 with V3 is orthogonal, U2 with V2 is not orthogonal because I is not equal to j, okay. So U2 will be perpendicular to V1 bar, V3 bar, etc. U2 is not perpendicular to V2 bar because it corresponds to the same eigenvalue, okay. So basically this set of eigenvectors that I have written is in the same order. These correspond to so now I am going to write down the property of the theorem that so these two sets I am going to say form a bi-orthogonal set. When I say bi-orthogonal set, I may have two sets with this property, okay. So basically I am saying Ui and Vj form a bi-orthogonal set. That means U1 with V1 bar is not equal to 0 because now the same eigenvalue I am looking at, but U1 with Vj bar equals 0 for j not equal to 1, okay. Similarly, inner product of U2, the second eigenvector is equal to 0 for j not equal to 2, but is not equal to 0, okay. I think when you do a couple of problems you will understand it. So this bi-orthogonality property is useful for us for calculating the coefficients. If it's if you have a basis which is orthogonal, we said we can calculate the coefficients by exploiting the orthogonality property, okay. But now I is not orthogonal because it's not self-adjoint. So I can't use, I have basically an independent set of vectors for a general case. So again, there is no point in using the eigenvectors as a basis, because they are only independent, which we will show now. So, but I can use this bi-orthogonality property to calculate these coefficients when I am expressing the unknown arbitrary vector in terms of these eigenvectors. Okay. So, I think it will become clear when we see it. So, this is basically what I am trying to say, that the eigenvector of A corresponding to a particular eigenvalue is perpendicular to the complex conjugate of the eigenvectors of A transpose corresponding to all the other eigenvalues. Okay. So, that is what I mean. To the okay. Consider a general matrix. What do I mean by general matrix? A is not equal to A transpose. That is what I mean by general matrix. Okay. I mean, not self-adjoint. And let us assume for now that we have n eigenvectors. Okay. Let us say we have n eigenvectors. I want to emphasize that I am kind of making an assumption, I will explain it later. So, I am going to make a claim that these n eigenvectors are independent and they can be used as a basis. Okay. So, therefore, these n eigenvectors are independent and can be used as a basis, which means any vector in Rn can be expressed as a linear combination of this basis. Okay. What is the meaning of this? This means any x belonging to Rn can be written as sigma Ci ui. That is what it means. When I say ui is a basis, I mean I can take any vector and write it as a linear combination. Only point is, now this is not orthogonal, because I am talking about general case, this is independent. Okay. Now the question is, I want to show that if I have n eigenvectors, I want to prove that they are going to be independent. Okay. That is the thing. Just because you have n vectors does not mean they are independent, right? You could have dependency. If I have n eigenvectors, what is the guarantee that they are independent? Okay. So, we will prove this by contradiction. We want to prove by contradiction. Contradiction means we assume that they are dependent. Okay. So, we assume they are dependent. So, I have u1, u2, ur plus 1, un. So, this entire thing is dependent, but that means the subset, some small number of those vectors form an independent set. Okay. So, I am assuming that let us say the first ur vectors are independent. Okay. Let first ur vector, first r vectors form a independent set. Okay. So, I have n vectors of these first r are independent, and therefore, all the others can be written as a linear combination of those, correct. So, what does this mean? This means ur plus 1 can be written as a linear combination of Ci ui I equals 1 through r, because the up till r is independent. So, any vector r plus 1 vector can be written as a linear combination if they are dependent. Okay, if this forms a dependent set, that means this can be written as a linear combination of this. So, that is what I have written. Ci is a non-zero number, that is what it means. Yeah. So, I am going to operate on both sides by a. Okay. So, a ur plus 1 equals a sigma Ci ui I equals 1 through r. Okay. And all the u's, remember, are eigenvectors. So, what is a ur plus 1? It is lambda r plus 1 ur plus 1 by definition. A u is equal to lambda u. Okay. So, this is okay, this I will write as lambda r plus 1 ur plus 1, and this is because the linear operator, by the definition of the linear operator, remember L times C1 U1 plus C2 U2 is C1 LU1 plus C2 LU2. So, I can take the A inside, C is a scalar, I can take M here. So, I can get this as sigma I equals 1 through R Ci A Ui, which is sigma Ci lambda I Ui. The other thing I can do is, I can multiply this whole equation by lambda r plus 1. Okay. I am going to multiply this first equation by lambda r plus 1. What do I get? Equals sigma I equals 1 through r Ci lambda r plus 1 ui. Okay. So, what I did first was just operated by a, and now I am multiplying by lambda r plus 1. What do I get? I get these two are identical, right? Lambda r plus 1, lambda r plus 1, ur plus 1. When I subtract, I will get 0. So, subtracting, I have lost track of my equation numbers. So, I think I will put 4 and 5 here, huh? Or to be on the safe side, I will put 5 and 6. Do not ask me where is 4, okay. 5 and 6, I am subtracting these two. I get 0 equals sigma I equal to 1 through r Ci lambda I minus lambda r plus 1 ui. Now, So I have 0 equal to this linear combination. This is my linear relationship. Go back again to what we discussed. And we have assumed, what did we assume to begin with? That the up to R is independent. Okay, up to R we started saying up to R vectors are independent, and we wrote the other one as R plus 1 in terms of this R. Okay. So now you see that the independent, that means this lambda I is not equal to lambda R plus 1. The lambda R plus 1 is after the first R. Okay. Lambda I is in the I is going from 1 through R. I is going from 1 through R, so lambda 1 minus lambda whatever, R plus 1, lambda 2 minus this. So this is not going to be 0. So only, and in order for this to be an independent set, only the trivial relationship has to be satisfied. That means Ci has to be 0. Okay. This means Ci has to be 0 for all I. I cannot get a non-zero Ci. Okay. And this shows only way this relationship can be satisfied is if Ci is 0. This shows that Ui I going from 1 through n form an independent set. Okay. So I took a subset and I said, look, that is independent, but if I take a subset, then I can write the ones outside the subset as a linear combination. So I mean, there's some thinking involved. You have to think about it. But I think it's most of the stuff that I'm doing on the board are reasonably 2 or 3 step processes. Okay, but you have to think and convince yourself that the arguments that I'm making are indeed correct. Okay, and if you don't think it's correct, you have to come and argue with me that I'm wrong. Okay, I'm willing to accept that, but you have to show me. But you have to think about it. Okay. So the point is, I mean, if I take capital R, I mean, and R can be anything. So basically, I have to go up to all the way up till n and show that this is independent. Anyway, so all these proofs are reasonably straightforward. Now, couple of small subtle points which I want to emphasize before we keep moving on. Okay. If I have an n by n if A is n by n, we are guaranteed n eigenvalues. Because the eigenvalues are roots of a polynomial, nth order polynomial, and that has n roots, real, complex, I don't care. But I may not have n eigenvectors. That's the reason I kept saying I'm assuming I have n eigenvectors. Okay, my number of eigenvectors can be less than n. Now, if the eigenvalues are all distinct in the sense they are not repeated, okay, if the eigenvalues are not repeated. They are only a single root, they are only occurring once. Each eigenvalue has a corresponding eigenvector, but okay, now we will have n eigenvectors. Well, the eigenvalues can be repeated. What do I mean by that? I mean, if I have a 3 by 3 matrix, lambda equal to 2 maybe occur 2 times. You have 2 eigenvalues, lambda equal to 2, and 1 maybe lambda equal to 5. That's what I mean. So the eigenvalues are getting repeated. Okay. If the eigenvalues get repeated, if eigenvalues are repeated, what do I mean by that? I'll just write the exact example that I said. Let us say you have a matrix for which the eigenvalues are 2, 2 and 5. Okay. Eigenvalue 2 is repeated twice or repeated once, whatever, occurring 2 times. But 5 is occurring only once. This can happen because these are roots of a polynomial. A particular root can be repeated, right? I mean, you can have a quadratic which has repeated roots. Okay. So you can have repeated this thing. Now the number of times it is getting repeated, that is called the algebraic multiplicity of an eigenvalue. So this is the algebraic multiplicity is the number of times an eigenvalue is repeated. Okay. So this 2 is lambda equals 2 has algebraic multiplicity. Let me add one more 2, man. You'll allow me, no? We have too many 2's here, so I want to have less confusion. Lambda equal to 2 has algebraic multiplicity. What is the algebraic multiplicity of 3? I don't want to have the same 2 everywhere. Okay. The geometric multiplicity is the number of eigenvectors which are associated with an eigenvalue. Okay. Okay. So you could have situations where you'll have 3 eigenvectors corresponding to lambda equal to 2. You may have less than 3. Also possible. Okay. So for lambda equal to 2, if we have only one eigenvector, then the geometric multiplicity is 1. So that's the difference between the algebraic multiplicity and the geometric multiplicity concept. Okay. And the number of eigenvectors is going to be decided by the rank of that matrix A minus lambda I. Okay. So, what decides the geometric multiplicity? The rank of A minus lambda I determines the geometric multiplicity. Okay. I think the easiest way for me to illustrate this is to take the identity matrix. Consider the identity matrix 1. I can make it complicated by doing a 3-dimensional 3 by 3. So, identity matrix means 1 is on the diagonals, okay, and you can calculate the eigenvalues for this. What are the eigenvalues? If you do the characteristic equation, this will be the polynomial which decides what the eigenvalues are, okay, and you can see that lambda equal to 1 is repeated 3 times. Equals 1 is repeated 3 times. So, algebraic multiplicity is 3. And what are the eigenvectors? Eigenvectors are 1 0 0, 0 1 0 and 0 0 1. We have 3 eigenvectors, 3 independent eigenvectors. So, geometric multiplicity is 3. Okay. But you can have some other case where an eigenvalue may be repeated 3 times, but the eigenvector will be only 2 or 1. So, for example, if you have the rank of this A minus lambda is, in this case it becomes 2, I will have 1 eigenvector. The rank is 1, I will have 2 eigenvectors. The rank is 0, I will have 3 eigenvectors. If you do A minus lambda, you get 0 as the vector, okay. That is the reason. So, for example, A minus lambda I, lambda is 1, remember, I get 0, rank is 0, there are no independent, everything is 0, okay. So, basically I have 3, that is the reason I am having 3 independent eigenvectors. This gives the 3 independent eigenvectors, but if this had rank 2, I would have got only 1 independent eigenvector. If I had got rank 1, I would have got 2, you understand. So, if this rank were 2, we will get only 1 independent, 1 eigenvector, independent eigenvector. Okay. So, point is, you could have matrices where the number of eigenvectors is less than n. Okay. Now, we are not going to bother about that in this course. So, you guys are all very lucky people. So, we are going to worry about other things in life, because then there are other more generalized concepts that you have to introduce. Okay. So, we will just for now, that is the reason I kept harping on, we are assuming that there are n eigenvectors. Okay. It may not be the case. If you do not have n eigenvectors, then you cannot use them as a basis, because in Rn if I have if n is 10, only 9 eigenvectors or 8 eigenvectors, I can only get a subspace of Rn. I won't get Rn, okay. So then I can't use it as a basis. So that's something you have to keep in mind. So, but we'll keep life simple, but you need to understand that just because you have a matrix which is n by n, you are not guaranteed n eigenvectors, you are guaranteed n eigenvalues, whereas if the eigenvalues are all distinct, there is no repeated eigenvalue, like in this case we had repeated eigenvalues. One was repeated 3 times, right. Lambda is 1, 1, 1. So this is repeated. Suppose I don't have repeated eigenvalues, then you are guaranteed n eigenvectors, but each eigenvalue will have one eigenvector. But if you have more than, if you have repetition, you are not guaranteed, you may have less number of eigenvectors. Geometric multiplicity will always be less, then you can't use it as a basis, okay. So that is basically the point I want to make. What we will do is, I can see a lot of blank faces. So what we will do is we will give an assignment, and when we solve the problems, you know, next time you come to class there will be brightness in all your faces, right. So we will send an assignment wherein you have to actually calculate eigenvalues, eigenvectors, and some of the theorems that I have proved you can actually work out by example, okay. Some of these the routine calculations, but I of course expect that you will do it by hand, and that is the only way to do it. What I want to do next is talk about, not today, the next class, talk about something called the solvability condition. Now you know that you can have you studied this in linear algebra, you talk about consistent equations, equations are inconsistent, right, and then you have no solution, things like that. So rather than talk in terms of rank of a matrix, rank of an augmented matrix and all that, we want to discuss the same concepts in the framework of adjoint operators, okay. That is what we will do, same thing, whatever you learned earlier, we are just going to discuss the same thing, but with a different angle. Thank you.